Hi, this video lesson is about two-dimensional motion, specifically talking about horizontal projectile motion. As we've previously looked at with one-dimensional motion, right, again, that motion either left, right, up, down, or north, south, east, west. Now we're looking at how does an object behave when it's moving in two dimensions at the same time. Previously looking at vectors, right, we get the idea that we get the resultant, which is going to give us, your overall displacement or your overall velocity. And it's going to be velocity because that vector is going to indicate which direction we're actually moving in. So here's a thought, right, and it kind of goes back to the riverboat example from the previous set of notes. If you have two identical bullets that are the same height above the ground and they're released at the same time, one is dropped while the other is shot horizontally out from a gun. Which one hits the ground first? Right now, take a moment and make a prediction. Same height, one is dropped, one is fired horizontally, so at a 0-degree angle. Which one will hit the ground first? Take a moment to make a prediction. Okay, now that you've made your prediction, right, what we're going to be able to see is that these two objects are going to hit the ground at the exact same time. Mythbusters does a pretty good look at this, where they actually do fire a gun and drop a bullet from the same height. I have provided the links to these videos right here. They're also going to be in the video lesson quiz for this as well, so feel free to watch those. They have the whole setup, and what we find is that they hit at the exact same time. And the rationale behind that is because a projectile is only influenced by the force of gravity, right? It doesn't propel itself once it has been launched. So for the bullet that's dropped, when it drops, the only force it acts on it is gravity. Same force acts on that bullet when it is fired horizontally. As soon as that trigger is pulled on that firearm, and that round starts to move, and the bullet begins to move through the barrel of the gun, it's a projectile. Nothing else is acting on it other than gravity after it has been fired. So it leaves the barrel of the gun, even though it has an extremely high horizontal velocity, it's still only being pulled down by gravity, which allows us to see, again, that independence of the horizontal component and the vertical component, which we touched on in the vector video lesson. Right? The idea that just because the projectile is being shot really fast horizontally, that has no bearing on what's happening to it vertically. Right? So gravity pulls down on that bullet vertically, whether it's dropped or whether it's fired horizontally. And it can't propel itself once it's launched, right? And that's the big thing here with a projectile. Once it is airborne, gravity is the only thing influencing it, and it cannot propel itself at any given point in time after. So examples of this would be an arrow, right? So you shoot an arrow. That would count. A bullet. You kick a soccer ball, kick a football, throw a softball, hit a baseball, hit a golf ball. You name it, if it is airborne and cannot somehow propel itself, it is a projectile. A calculator. If you get really mad and you throw your iPad because you're sick of it freezing, your iPad becomes a projectile until it makes contact with something. Things that are not projectiles, airplanes, self-propelled rockets, drones that are in motion, right? As long as the engines are working on these things, they're not going to be projectiles. Helicopters are another example. Yes. So with our trajectory then, so we're going to talk about the trajectory, and we're going to study how these objects move, right, and the path that they take. What we see for any projectile, so long as gravity is the only force that's influencing it, because that's how we define it, the trajectory is going to be the parabolic path that it's going to take. Now, when it's launched horizontally, which we're going to look at, it's only going to be half of that parabola. If you launch it at an angle, now we're going to get the full parabolic shape that we're going to see. So in Unit 1, right, we looked at horizontal motion and vertical motion in one dimension. Now for a projectile, we just combine these two. So we can look at what is this object doing horizontally, what is it doing vertically, and we can predict with a very high degree of accuracy where an object will be horizontally and vertically at any point in time. We can pinpoint its location using the exact same one-dimensional motion formulas from the previous unit. Right? And that's because the variables are the same, but now you really have to be good with your horizontals and your verticals. So if you notice the bullet point to the right, delta x and delta y are very, very different. They're going to yield two different things. Delta x will be your horizontal displacement, where delta y will be your vertical displacement. T is still time. We still have Vyi and Vyf, our initial and final vertical velocities respectively. But now we can isolate the horizontal velocity and just refer to it as v of x. Note that we don't have an initial or a final horizontal velocity. It's just Vx. We'll get to that in a second. And there's no a, right? There's no horizontal acceleration. But we still have g, which is our vertical acceleration, that negative 9.81 meters per second squared. So really do a nice job here of separating and isolating your horizontal and your vertical components from one another. Because they're at 90 degrees, they're perpendicular components, the motion vertically does not impact the motion horizontally and vice versa. Now, we're going to get into components here, and we saw this with the vector stuff. Because we have this combination, we're going to look for the horizontal component or the vertical component of something, right? And a component is simply just a very specific value in a very specific direction in this context. Rather than looking at the big, grand scheme, the component is what is the small bit of information that I know that can help me describe the overall motion that I see. So our vertical motion is still free fall, but now it's free fall moving horizontally, because remember, free fall can be up or down. Well, an object can be moving up or down and left and right at the same time, right? So we have a horizontal component to that vertical free fall motion. By breaking it down into its individual components, we can truly see how high is this thing going to reach, how fast is it moving vertically, how fast is it moving up or down, and we can be able to tell, well, how far away is this thing going to land? How fast is it going to get there? How fast will it be moving when it hits the ground? So for the horizontal using components helps us. This is the lone horizontal formula that we have for projectiles, because we ignore air resistance and we ignore wind and we ignore any air friction, right? Which truly means that the only force that we get is gravity, which is a vertical force, not a horizontal force. Because of that, forces cause objects to change their motion. So if we have a vertical force causing the object to change its motion vertically, that's where we're going to get the acceleration from. We don't have any horizontal forces acting on the projectile. And that's true on any angle. So because of that, there is no acceleration horizontally, which means our horizontal velocity stays constant. So if you launch a projectile horizontally at 10 meters per second, that means at any point in time, the horizontal velocity is 10 meters per second through the entire flight. Now, vertically, that velocity is going to change, but horizontally, it won't. So because of that, no force acting on it, we have no acceleration, which is why we don't see a as one of our variables here. So the initial horizontal velocity will not change. Thus, the only formula that you need to worry about for a horizontally launched projectile, or really any projectile launched at any angle, is delta x equals v of x over delta t. Basically, your velocity, v of x, is delta x over delta t. It comes down to your definition of velocity. How is its displacement changing horizontally? How long is it taking to get there? And that's so we can find that horizontal velocity. So this is it, horizontally. This is it. This is the only thing that you have to worry about. Vertically, on the other hand, things are a little bit different. And if you notice on these formulas here, none of them include the initial vertical velocity, right? So our vertical component, when it's shot horizontally, looks different than when it's shot at an angle, right? When we're shooting at 0 degrees, which would be horizontal, there is no initial vertical velocity because we consider a horizontal, a 0 degree launch, to not have a vertical component at the start. So each one of these three formulas does not have VYI because the initial vertical velocity is 0. So that term goes away, and anything that it's being multiplied or divided by as well cancels out. So if you go to your free fall formulas from last unit, they're the exact same ones, just because we're at a vertical rest, since it's shot horizontally, there is no initial vertical velocity, all those VYI terms drop out. We can simplify all those formulas to here. So when we shoot something horizontally, our horizontal velocity stays constant. Delta Y is going to be that height. Delta X is what we would consider the range, right? How far away does something get versus how far does something fall, right? There's kind of some terminology things that you need to look at. But one thing that's nice to notice here is this is a true half of a parabola. Because we have that acceleration vertically with a constant horizontal motion, we get this parabolic path. And it's, again, due to that independence of the vertical motion and the horizontal motion. So we get the parabola to be able to represent our motion. Time becomes critical here, right? Time is arguably the most important thing that you can look at in terms of any projectile motion. Because if you want to go from, hey, how is it moving horizontally to how is it moving vertically, the only common variable that they have is time. And think about why that works. The time it takes for something to go horizontally will be the same time it takes for it to drop vertically, or in the case when we launch at an angle, to move upward vertically as well, right? Because that horizontal motion is going to have a time to it. The vertical motion is going to have a time to it. So if you can find out what that time is, that is going to really help you be able to bridge from vertical to horizontal or horizontal to vertical to be able to solve the entire projectile to figure out exactly where it's located, both vertically and horizontally, and how fast it is moving, both vertically and horizontally, and what direction it's moving, and what angle it's at, right? So we can solve the entire projectile if you know time. Have to be able to get to time, folks. So there are some of your concepts with two-dimensional motion, projectiles that are launched horizontally, which should be launched at a 0-degree angle.